we are starting from the Joule heating. So this kind of phenomena occurs whenever an electric current flows through a material that has some resistance, and then as the result it creates a heat. So at this moment we are talking about the resistive heating, which is the result of friction, a friction which is created by microscopic phenomena from collisions of the electrons, and the heat which corresponds to the work done by the electrons is traveling to a lower potential, makes them traveling to the lower potential. So in this thing we can define this Joule heating, and as you see, inputs include current, voltage and material resistivity. So we have these three parameters, and the most important one is the resistivity material property, which can be defined as the resistance, as the product of the resistance and the cross-sectional area divided by the length of the part. So as I said, this parameter is required for any solid that is heated by the Joule effect. And there are many practical uses of Joule heating. So for example, electric stoves and other electric heaters usually work by Joule heating. Soldering irons, cartridge heaters, electric fuses, they are the examples. So for example, if we talking about the electric fuses, they rely on the fact that if enough current flows, enough heat will be generated to melt the fuse wire. So if we take a look on this slide again, this feature basically is related to the CFD analysis, but the Joule heating has been also provided for a structural module, and we have a few new analysis types. So for example, we can perform nonlinear steady state Joule heating, nonlinear transient simulation, and of course we can add some thermal stress simulations for the simulation of this effect. So the input is almost the same, but this time this electric potential has been defined by conductivity, which is reverse definition of the resistivity. So again, this is exactly the same parameter.